And welcome back to Transparent Physics. In this lesson, we're going to be solving equations from the gravitation and orbits unit. This one about satellite mechanics, the speed and velocity with which satellites will orbit a central mass. And in our last video, we talked about Ceres, the largest object in the asteroid belt. It is also the 25th largest object in the solar system, if we include objects within the orbit of Neptune. And so Ceres has an average orbital radius of 4.14 10 to the 8th kilometers. Now this is its orbital radius, not its individual radius. There is the radius of the object itself, and then there's the radius of the object's orbit. Be careful you don't get those two flipped. They're both going to be the same units, easy to do. Just make sure you're aware of what piece of information you're being given. Knowing the sun's mass to be 1.99 10 to the 30th kilograms, that's a big value. What must Ceres' orbital period and speed be? I wrote velocity initially. I scratched that out because velocity is speed and direction, and with these problems we are not worried about the direction, we are just worried about the speed at which it travels. So if I occasionally say orbital velocity, I do apologize. I should be saying orbital speed, but I make that mistake sometimes. Okay, and it's a problem solving session, so you know what that means. Now the last problem, I ate banana chips, and I got more banana chips. I got the same. This is I'm filming 2 lessons back to back. And I got a big bag of banana chips from Aldi's, so I'm going to keep eating them. Now, these banana chips are a little smaller because they're a little closer to the bottom of the bowl, but that's okay. So I read my question. And let's get this underlining done. Now, sometimes it's easy to get distracted by a number. Don't underline 25. It's just there to distract you. Just because it's a number doesn't mean you have to underline it. We do have average orbital radius, that's an R. This is the central mass, the mass of the sun. And watch out here, they actually snuck in 2 questions. They're asking for period, and they're asking for speed. So if you weren't reading that carefully, you might miss that they're basically asking you to solve 2 problems, even though they're not saying A and B. All right. We did our underlining. Now, in terms of information, we're just going to default this into an A and a B. We'll just make it into an A and B ourselves. All right, for part A. Now, also in this scenario, now's a good time to stop and take a sip of tea. All right. You don't need to draw 2 different diagrams. The diagram you draw is going to be good for everything. So, in this case, we're going to draw the sun. And then way out here somewhere is Ceres. I would draw the rest of the asteroid belt, but I don't want to get distracting here. So, all right. So, we know the average orbital radius to be 4.14 10 to the 8th kilometers. And we know the mass of our sun to be 1.99 10 to the 30th kilograms. And we are interested, as Ceres orbits around, we are interested in its period, and we are interested in its speed. One thing before we move on and pick our formula, we want to ask ourselves if the units are appropriate. Here they snuck in kilometers. We cannot use kilometers. The carefree days of using whatever unit we wanted with Kepler's third law are gone. Lost like tears in the rain. Now we must go back to our base SI units. So we're going to have to convert 4.14 10 to the 8th kilometers to meters. Again, not too terribly hard to do. I know the instinct for a lot of people is to just sort of do it in your head. I mean, I respect that, but in the same regards, it's easy to screw stuff up when you do it in your head. You just write it out, you're good to go. Kilometers cancel with kilometers, multiply by 1,000. Multiplying by 1,000 is increasing the exponent by 3. So it would be 4.18 10 to the 11th meters. All right, now we're ready to go. So that's our information. And let's pick our equation. The first one involves the orbital period. Realistically speaking, I would always just start with Newton's version of Kepler's third law. I think that's a pretty flexible equation. That said, yeah, I mean, if you want to just go right into the orbital period equation, that's totally fine. I get it. But I don't know, I kind of like to have a fewer equations that are more flexible than a lot of very specific equations that are only good for certain circumstances. But in this case, I want to solve for the period. So I take the square root of both sides, so it becomes t equals the square root of 4 pi squared r cubed over gm. And when we write it like that, we often pull the 4 pi squared out. And the square root of 4 pi squared is 2 pi. I don't know. Does that make the problem appreciably easier? I don't know. It's just kind of tradition. That's the way we do it. And I think we've got our procedure established. Everything's ready to go. We just need to plug and chug. And procedure cleared. Oh, yeah. I'm going to save the last banana chip. This is a two-part problem. I'm going to save the last banana chip for part B. But don't let me forget to eat it. So we have 2 pi square root. Don't forget to use our converted orbital radius. 4.18 10 to the 11th meters. Divided by 6.67 10 to the negative 11th newtons. Meters squared per kilograms squared. And the mass of the sun is 1.99 10 to the 30th kilograms. Now when you're writing it's so big I'm off screen. When you're writing lots of big values like that, it is easy to make some mistakes. So for instance, take a look at this. Everything looked good for you guys, right? It's a 30, by the way. Everything look fine? Are we, as I come back into focus, are we ready to go? Just plug and chug, right? 5, 4, 3, 2, 1. The answer is no. And if you caught the fact right here, this is r cubed. Very easy to forget to write r cubed on the next part. So that does need to be cubed. Okay, this is a bit of a mess to solve, to plug it into your calculator. Again, I'm always a fan of doing the whole thing at once, but you can break it up into parts. Multiplying by 2 pi is probably not the worst thing to do, just to wait, till it's all said and done to do it. But if I was to plug this into my calculator, if I was to do it all at once, and again, I'm a big fan of doing everything all at once, just so you don't have to worry about rounding or writing things down or anything like that. So you could say, starting over here, I think I'll have enough room if I start over here. If you just type 2 pi, your calculator should just multiply those together automatically. And just for, all right, multiplication symbol. Then however your calculator does it, you're going to want to open your square root. Now when you're using a calculator like the TI 30X2S, when you open the calculator function, when you turn it on, when you open the square root, it comes with a free parenthesis. Just remember that. That is a point of confusion. A lot of times I see students when they're trying to figure out the right number of parentheses. This is a free parenthesis, but when you close this parenthesis, you do the square root. So don't close this. You can add other parentheses on the inside, but when this parenthesis gets closed, we're done. All right, and I'll try to show you an example of that as we go through. So you get a free parenthesis in there. So I'm going to write 4.18, and I'm going to use my, for the TI-32X, it's, we want to get our scientific notation in place. So for the TI-32X, I would press the second button, and then I would press X to the -1, and that gets our scientific notation triggered. And that is to the 11th power. Now this whole quantity should be taken cubed. That exponent factor is going to trump everything, and probably just to be careful to make sure it doesn't inadvertently say cube the 11 instead, we should probably add our own set of parentheses in here. Get that guy isolated, and then take that to the 3rd power. Okay. Then we're going to divide, and I actually looking at this, I do not think I'm going to have time to. I'm going to run out of space. All right. Now, big thing here when we're dividing and we have 2 objects in the denominator, you have to be super careful, because the temptation would be to just say divide by this times this, and it'll divide by this and then multiply everything by this. You have to keep the denominator locked together. In fact, here I'll even color code it to make it easier. We have to keep these guys together when we solve this out. So I'm going to drop down a line, and I'm going to add a parenthesis. It's going to be 6.67. I'm just going to write E for the sake of simplicity. Oh, look at this. This is 4.18, 10 to the 11th, and this is 6.67, 10 to the -11th. How interesting. And then we multiply by 1.99. And there's no squares here or anything like that. And then we can close that parenthesis. So the basement is done. And then this parenthesis is already closed out. And this parenthesis will close for free at the end when we press the square root button. So, or we press enter. I'm going to zoom out a little bit so you guys can follow me doing this one. That's my last bit of image. All right. All right, so it's going to be 2 pi times the quantity square root. And again, we're going to open that next parenthesis just in case. I mean, technically, I could go and actually see whether or not that's going to be a problem. But as long as you're careful with your parentheses, it won't make too much of a difference. That's 4.18, e to the 11th. That's right there. I'm going to close that out. And then I'm going to take that to the 3rd power. And then I'm going to divide, add another parenthesis. That's the green parenthesis. 6.67 e to the -11th times 1.99 e to the 30th. So you can see this is quite a it's quite a lot to enter in. And I could close the last square if I close the last parenthesis if I want to. That's going to block off the square root. Again, the calculator will do that automatically for you if you don't. And we're going to go, and what do we get? That, my friends, is ugly. But that's the answer. That is 1.47, let's say 1.474. And that is 2, 4, 6, 8, 10 to the 8th. And what did we just solve for? Well, this is the period. And remember, we're out of Kepler's third law, so everything's got to be back in terms of SI. So what we just solved for is an answer in seconds. Now, that's not terribly helpful unless you've got some interesting choices in memorizing random numbers. But we can convert that to, say, years pretty quickly. So we have, let's say, 3,600 seconds in 1 hour. And 24 hours in 1 day. And 365.25 days in 1 year. just to be a little more precise about it. So when it's all said and done, how many years is it going to take Ceres to orbit? It should be more than 2 and less than like 8. It should be somewhere in between there, I would imagine. Let's take a look. So, solving that out, it's 1.474 e to the 8th divided by 3600 divided by 24 divided by 365.25. There we go, 4.67. So Ceres takes around 4.67 years to orbit the sun. And victory celebration, right? We're done. Eat that last banana chip, and the answer is no. All that was only the orbital period. So let's get that orbital velocity, I don't see, I did it right there, orbital speed. All right, so that's part A. Part B is the orbital speed. Equation for orbital speed is the square root of big G, big M over R. So that's 6.67, 10 to the negative 11th, Newton meter squared per kilogram squared. 1.99, 10 to the 30th kilograms. And we divide all that by the orbital radius. Don't forget to keep the meters value. 4.18, 10 to the 11th meters. So it's kind of a plug and chug, but it's a pretty hard plug. I'm not going to lie about it. So that's going to open your square roots. Get a free parenthesis when you do that on the TI-30X2S. Get our E on there. Negative 11 times. And these values we've all seen before now. Now, for the last step here, do I need to put a parentheses at the bottom here? The answer is no, because there's only one term. So it can multiply this by this and then divide by that. When you have multiple terms in the bottom, you got to watch out that it doesn't divide by the first term and then multiply by the rest. But here we're okay. 4.18 e to the 11th. And again, there'll be a parenthesis at the end, but you can add it if you want to. I don't have any real sense for how fast Ceres should be traveling through space, and I don't imagine you would either, but hopefully we'll just get the right answer. We'll be okay. All right, 6.67. Ooh, hello. E, the negative 11th. That's 1.99 e to the 30th divided by 4.18 e to the 11th. And that's 17,000, let's say 800 meters per second. And that is its orbital velocity. Speed, orbital speed, orbital speed. All right, so we have our period, and we have our speed. And there we go. Again, easy to do? No, but also a short solution, aside from actually plugging it into your calculator. But getting there often is pretty expedited, pretty fast to do. Like eating this last banana chip here, that's going to be pretty fast to do because it's a small banana chip. All right, I'm going to press pause, get myself set up for the last problem, and then we'll pick it up again. Okay, we're back. Did you know that in 1977 we didn't know that Pluto had any moons? We thought Pluto was just Pluto. How did we find out that Pluto had moons? Well, there was an astronomer named James Christie, and he was studying photographic just records of Pluto, and he noticed over time that occasionally there appeared to be a small bulge. I mean, very, very small bulge but it seemed to appear periodically. And so or Dr. Christie, I guess, probably said, hey, I wonder if Pluto has a moon. And turns out it does. Actually, Pluto has a couple moons. But this newly discovered moon was called, and there's always a bit of debate on how, Charon? Charon is the, it's pretty cool actually. Pluto is the god of the underworld. And again, all the planets are named off mythological creatures, or, well, mythological deities. And Charon is the fairy. He drives the ferry to the underworld, so he's the guy who delivers people to the underworld. So pretty cool. They named him for that. And I think it actually came from a science fiction story earlier where a guy proposed that Pluto had moons. So a couple neat ways to tie that in. In any case, once we saw there was an object orbiting Pluto, we actually could learn more about Pluto because we can use our equations by analyzing the motion of a satellite. We can learn more about the object itself. So when we take a closer look at Charon's orbit, it has a period of 6.39 days and an orbital radius of 19,591 kilometers. And we can actually use that to solve for a estimate of Pluto's mass. So let's give it a go. What do we know? 1978, a number, but not an important number. I mean, it is if you were James Christie, but... And they actually were very nice to us. They actually assigned things to variables for us already. And we're interested in the mass of Pluto. And they even told us, use Newton's version of Kepler's third law. Sometimes the problem will even tell you what equation to use, because there might be more than one approach, and they want you to demonstrate your talent with a specific equation. So we have underlined. So next up, let's get our picture ready to go. So you have Pluto, and we have Charon. Actually, Charon's big enough that some people actually consider this almost to be a double planetary system, because compared to the mass of Pluto, Charon is actually pretty big. So they actually kind of orbit. This guy doesn't actually orbit. Specifically, the planet, the center of orbit is actually outside of Pluto. They actually sort of swing each other around. All right. So orbital radius, 19591 kilometers. They did it to us again. Can't use kilometers. They did it to us again. 6.39 days. We can't use 6.39 days. So we have to convert both those into SI-friendly units. And we're interested in the mass of Pluto. All right. So let's do a little unit conversion. On the top, kilometer goes on the bottoms. Meters goes on the top. For the next guy, I think I'm going to have to do this in 2 steps. 1 day is 24 hours, and 1 hour is 3,600 seconds. So we got to get all those things worked out before we can get any further. So 19591 times 1,000. Still going to be 1.9591, but it's going to be, what, 2, 4, 6, 7, 10 to the 7th meters. This would have been, if we wrote it in scientific notation to start, this would have been 10 to the 4th. So you add 3 to it to get 10 to the 7th. And then for the time, how many seconds is 6.39 days? I feel like it's a musical of some sort. The guy has like 6.39 days to get the girl to fall in love with him or something like that. I don't know. They sing a song about the number of seconds. It would be, the hit song from the musical would be 552,096 seconds. I don't know if that would be a hit or not, but 5.52, 10 to the 5th seconds. Okay, now we have everything ready to go in our SI units. Quick tea break. Okay, we got all of our information established. I for information. Next up, how are we going to match these to each other? Well, it tells us the equation to use, so bonus for us. It tells us to use Newton's universal law, or Kepler's, third time's the charm, Newton's version of Kepler's third law. Now, this is a bit of a pickle because m is in the bottom, and we need to solve for m. So we need to get m out of there. Isolate m. I would multiply by m to start. I always like to get things out of the basement to start. So it's mt squared equals 4 pi squared r cubed over g. And then I want to get m by itself, so I divide both sides by t squared. So m is by its lonesome 4 pi squared r cubed over gt squared. And we're good to go. Now again, that's a messy thing to type stuff into, but that is that's the manipulation we're going to need. So 4 pi squared r cubed 1.9591 10 to the 7th meters. Don't forget to cube it. Divided by g, 6.67. Sometimes I want to write 6.61, but I think that's just the negative 11 talking there. Newton meter squared per kilogram squared. And the time, the period, 5.52, 10 to the 5th seconds. And that also gets squared. Okay. Now, getting that plugged in and ready to go is no easy task this Sunday drive. We take 4 times pi, and your calculator should have an x squared button. So that's 4 times pi squared times, this is a big one. Let's put this in parentheses just in case. Because we're going to cube this whole thing, and I just want to make sure I'm not accidentally cubing the 7 instead. I mean, again, I could try it out, see what happens, but it's not going to hurt to have an extra parenthesis in there. Okay, so that's the top. And then remember at the bottom, we're dividing by a denominator that is a product of two objects. So we got to make sure that those stick together. So we're going to divide, and then we're going to add parentheses here to make sure this all stays together when we plug it in. Now again, you are absolutely welcome to take the top and figure it out, and take the bottom and figure it out. Oh, that's an E. The only thing I find is that when you do that, you're going to be writing things down and rounding them, and then you got to plug them back into your calculator, and you could round wrong or write wrong or retype in wrong. So it is definitely more work. It seems to plug all this stuff in at the same time. But the bonus is that you don't have to worry about rounding or anything like that. It just gets all done. All right, so if we're squaring that thing on the bottom, okay, off camera, through the magic of technology, I paused it and I tried out whether or not it affects it if you put this in parentheses or don't. And it turns out the calculator is smart enough to realize that if I just put an x squared there, it is not going to square the 5. It's going to square the term. So the exponent trumps everything. The argument would be that if we would need it to square the 5, we would have to put that in parentheses, and the parentheses would trump the exponent. But here, the exponent trumps everything else. So, you putting an extra parenthesis in there is not going to hurt anything, but it is an extra step that apparently we do not need to do. So, and again, you can always learn a little bit more about skills as we move through things. And we're ready to go. That's the procedure all set up. Now we just need to plug and chug. All right. And action. 4 times. I missed a pi in there. 4 times pi squared times the quantity. Open square root. 1.9591 e to the 7th. That quantity. All right, we're gonna go for it. We're not gonna put those parentheses around the top. 1.9591 e to the 7th. That term cubed divided by green parenthesis 6.67 e to the negative 11th. If your calculator has memory buttons on it, I mean mine does, but it probably wouldn't hurt to put that into the memory of your calculator so you don't have to enter it in every time. 5.52 e to the 5th squared. No. All right. So we get the mass of Pluto to be 7.59 10 to the 11th kilograms. Is that right? Well, got my little pocket computer right here. I wonder if you can even ask Jeeves anymore. All right, I'm going to just type in mass of Pluto. And we are way off. All right. So the mass of Pluto is 1.309 10 to the 22nd kilograms. And we got 7.59 10 to the 11th kilograms. So this is a good thing to actually see, because now we have to troubleshoot where we went wrong. The temptation, of course, is for me to edit this out and get the right answer right away and make it look like I never make a mistake. But we made a mistake here somewhere. We've got to figure out where that is. So this is an excellent piece of excellent little object lesson here, because you are eventually going to have to figure out what you did wrong too. So you might have been watching this video and you already figured it out. Let's see. So 4 pi squared, 10 to the 7th. That is the, right now I'm just looking to make sure all the values work out. 10 to the 7th meters is the radius of Charon's orbit. We've got G, we've got T squared. Everything here is ready to go. Let me see what I plugged into the calculator. All right. So going through what I entered in my calculator, I believe I found my mistake. So when we plugged 4 pi squared times the quantity of 1.951 10 to the 7th meters cubed, I I put a square root in there. So I dropped a square root into this calculation, and there is no square root in the calculation at all. So I just simply made a mistake when I was typing it in. So sorry, that's not more exciting than that. I'm going to clear that little guy out of there. Boop. And then honestly, when we're done now, and there we go, way closer. So I got the new answer, the new and improved answer, is 1.46 10 to the 22nd kilograms, which is pretty close to the actual value of 1.31 10 to the 22nd kilograms. The difference would be just in terms of the actual values that we're using for the answer. So we'll get a little bit of rounding error in the fact that we're not using the exact value in notations, and it's a little more complicated than just a circular motion. All right, but when that's it, that little mistake there is okay. You always go back and check to see if your answer makes sense. This mass was way too small, so we needed to check to see why it was wrong, and then we fixed it. So it's okay to make mistakes. Just learn from them, and then we'll avoid adding superfluous square roots next time around. Okay, thank you for joining us for this solution set for gravity and orbits, and I hope we've had the opportunity to make physics a little clearer for you with transparent physics. Oh, and hey, I forgot. One banana chip left. I think we got our solution. We really earned it that time, didn't we? All right. Hey, everyone. Have a good one.